Hello, I'm back once again. Today I'm taking a little bit of a change of pace in how we do things. And I'm going to be discussing primarily this little proof that Reef gives in section 3.8 of his textbook, which discusses the dependence of the density of states on external parameters, right? So since the beginning of this particular book, Reef has discussed in detail how things like thermal equilibrium might affect our parameters, like pressure, volume, work, so on and so forth. Not necessarily work, but things of that order. And then he begins to beg the question in 3.8, what if we consider some sort of mechanical interaction instead of some sort of thermal interaction? So he says, let's just start off by picking some sort of single parameter, x. And x here can vary, right? So the number of states that our system will have between our desirable energy levels, E and E plus some small amount delta E, so some really small sliver of permissible energy levels, can be given by the function omega of E of x, which is also can be written as the sum over of omega E of x over all y. Now y is just some other variable that we have picked and we will be making use of throughout the course of this particular proof. Seems I have a visitor. You got a cameo. It wouldn't be a physics video if there wasn't a cat in it. Anyway, I'm sorry, sweet pea. Go. Okay, you're gonna do the proof with me when I'm holding you now. So that means I get one hand for the rest of the video. Anyway, so the thing we're interested here is a change in some sort of mechanical process, right? So if we're looking at our variable x, which is a parameter representative of that mechanical process, we need to ask, how does this particular parameter change from x here to some small incrementation of x plus dx, right? So we have to look at primarily this other function that he defines being the number of states that obtain a certain energy greater than E and sits in between E and delta E after starting some energy level below that, right? So this just counts the number of states that get brought up into our permissible energy range, essentially, right? So in order to count that number of states, or like how many of those states exist whenever we make this mechanical change, we have to look at the change in energy. Specifically, these states are given by a change of energy with respect to our mechanical parameter set equal to a value y, and that has the caveat that y changes some small amount y times dx, right? So now that we have that out of the way, we can actually start getting into the big ugly stuff down here. So delta E can thus be given, not delta, I'm sorry, sigma E. Once again, I reiterate, I should not teach Greek. Sigma E is thus given by a total number of states divided by unit energy, right? So we have our sigma sub y term divided by our small incremental change in energy times our small change in our mechanical parameter y dx, right? Our total, our overall, is given by a sum of these states over y. Now, Reef makes quick use of the fact that we can actually express y bar here, or an average of our parameter y, or expectation value of our parameter y, with this formula here, which is just your standard, expectation value formula. You have some probability of that function divided by the number of total states with that function, so on and so forth. And he just substitutes that into here. By extension of that logic, if our parameter y is equal to the change in energy with respect to our mechanical parameter x, then our average value of y should be an average energy with respect to x. And Reef makes a claim that this is actually equal to the negative average of our parameter x itself, which you'll come to see is a force conjugate later on down the road. Oh, actually no, he actually just declares it right here. X bar is, by the definition of equation 2.96 in your books, if you're following along, the mean generalized force conjugate to the external parameter x. So, he makes a little pivot saying that we need to begin reconsidering the total number of states, omega e and x, in our permissible energy range. So whenever we make some sort of change in the number of states, omega here, right, this has to be represented by the change in states we've brought up to our value E, the lower boundary of our energy range, to the higher end of our energy range, right? So once we have that, we can actually represent this as another partial derivative, but I know this is kind of hard to see. We take the difference between our sigma with an argument of E and our sigma with an argument of E plus delta E, and we can write this actually as being the negative partial differential of sigma with respect to E times some infinitesimal change delta E there, right? So once we have that, we have to evaluate our derivative a little bit further, right? Because we have, you know, par omega par x. What does that mean? We can also have, because it's a function of it's a multivariable function, we can take this partial derivative with respect to E. So we actually have to go out and do that now to see what these terms evaluate to in order to assess our statement here. So when we take our partial derivative with respect to E of omega, we get that it's equal to the negative partial derivative of our energy of the product between omega and y bar, right? Moreover, if we look at our partial differential of omega with respect to x, which is what we have here technically, we actually get that it is equal to the negative partial differential of omega times, not times, but with respect to energy, times y bar minus omega times the partial differential of y bar with respect to energy. We just apply the product rule, essentially, right, whenever we do this sort of thing. So once we have this expression, we just divide both sides by omega, and this statement, whenever we do that, we divide both sides here, we get a 1 over omega times a partial differential of omega with respect to x. That is analogous to the partial differential of the natural logarithm of omega with respect to x, if you remember your rules from calculus. And then, because we're taking a natural logarithm here, we get that same 1 over omega thing here as well. And then this transforms this term into a natural logarithm as well. Right, let me just write it out again here. So if we have, let's say natural logarithm of x r x is equal to 1 over x rx, right, from calculus. But we always just mark that as equal to 1 because, you know, the partial differential of x with respect to x is 1. But that's just the rule that gets applied. Just trying to, you know, clear up any sort of gaps in the knowledge. So we get that same natural logarithm behavior here multiplied by y bar, and then we get we subtract off the partial differential of our y bar with respect to energy. Now Reef makes the caveat that we can simplify this particular system by saying that our system is relatively small. So this term ends up basically just going to 0. It's too small to worry about. It won't really cause any sort of major change in our system as a whole. So what that leaves us with is that our partial differential of our natural logarithm of our state omega with respect to our mechanical parameter x is equal to the negative natural logarithm of omega with respect to our energy times our value y bar, and then that itself, because we've already defined what this is equal to beta times our average mechanical force conjugate x. So in general, the rule is that we can say that the natural logarithm of omega's partial differential with respect to some mechanical parameter x sub alpha is equal to beta, the temperature, times our generalized force conjugate x bar alpha. So from this we can actually get some pretty important results. Something like with pressure or with volume, for example. So you might have, I believe it's the partial differential ln omega par v of the volume is equal to our average pressure times our temperature beta. Because you can have some sort of mechanical parameter, and then we get some sort of force conjugate as a consequence of that particular derivation. I think I actually might have, since I'm here, a slightly easier to understand derivation of one of these force conjugates. Let me pull it out of my notes here. Okay. So let's say, for example, we want to derive pressure from volume. We want to derive this. That might be a little bit easier to see an example, because, you know, I believe that theory is important, but it doesn't exactly help you whenever you can't see how to apply it. Physics is useful to that extent, I think. I think it's good to have generalized theorems about things, but it's just kind of hard to see what the heck you're talking about unless you see an example in action, right? Okay, my cat's got my notebook. There we go. She's being very terrible today. So, let's say we want to get force from volume, okay? We can start here by saying that our derivative of our energy is equal to, with respect to volume, is equal to our partial derivative or energy with respect to volume, right? And then this can become, we just divide both sides by dV, we get dE is equal to partial dEr over the partial of V dV, right? Just some simple division. Now we have our dE term, which whenever we see dE or something along this equal to something, it should ring some bells in our brain to go, let's apply the first law. And the first law, in its inexact differential form, is d omega, not d omega, dw. I've been writing omega too much, now it's dw or c omega, is equal to negative dE plus dq, right? We don't have any particular change in heat here necessarily, or if we do, when we're only looking at an incremental change in the energy, we really should only have an incremental change in heat, if any at all, so we can actually neglect this term altogether. Say that goes to 0, and we're just left with the negative differential of E, right? So, if that's the case, then we may express the following, that our but our derivative of E with respect to the volume is equal to the partial derivative of E with respect to the volume. And the nice thing about this is that a change in energy over change in volume is simply expressed as being a negative change in, or negative pressure value being equal to our partial. Right? And we can get this from what we know work is equal to more expressly. So I should have written that first. But yeah. could say that from work, work is equal to P dV, right? And if we isolate P by itself, we get that P is equal to work divided by a change in volume. And if our differential of work is equal to a differential in energy, then this is basically analogous to saying that our pressure is equal to dE over dV, like that. That's what that comes from. But this p-value remains negative because of this relationship here. So it would be, just going to keep the negative in there. So, my cat loves throwing herself off places. So, I think I'm going to cut this portion actually. Try to see where it goes.